Welcome to our first Physics 2213 lecture video. I'd like to begin where it all begins in the theory of electromagnetics, namely Coulomb's law. So let's just recap what we probably are all very familiar with, perhaps from high school in terms of Coulomb's law. Recap of Coulomb's law. So when you're first introduced to Coulomb's law, and you might want to leave a little space on your paper if you're taking notes along with these videos, because I'm going to put in a series of different subscripts. But when we're first familiar with Coulomb's law, you find it in the form that the force between two different charges, and I'm leaving a little bit of space down in here because I'm going to put some subscripts, is equal to some constant times the product of the two charges, Q1 and Q2, divided by the distance between them squared. That's normally how it's stated. I'd like now to get a little bit more precise about Coulomb's law, because it turns out, in the end actually, that everything in this course comes from Coulomb's law. If you're willing to believe Coulomb's law based on empirical observations, and if you take seriously the implications of special relativity, and a special philosophical concept we'll come across a little bit later on in this lecture, something known as action at a distance. If you're willing to take all of that seriously, then you can actually derive, just from Coulomb's law, all of electromagnetic theory, including the consequences of magnetism and the theory of light. So it really behooves us to try to understand in very good detail the precise nature of Coulomb's law. So to allow ourselves to do that, let me put down some precise definitions of exactly what the situation is that we're trying to study. So what I'm going to imagine is that I have my two charges, and I'm going to call them, as I had already, Q1 and Q sub 2. And now those are going to be sitting at certain locations in space. So I'm going to need an origin. I'll call that origin O. And then there's going to be a vector position for charge Q1, and I'll call that vector position R1. And then there's going to be another vector giving me the location of charge Q2, and I'm going to call that vector R2. Very good. Now, the force between these, we have to be a little bit careful. Let's just imagine these are both, say, positive charges. We know then that what will happen is they will repel each other. So there will be a force on Q2 that's directly outward from the pair in this direction. And there'll be a force from Q1 directly outward or away from Q2, which will be in this opposite direction. So the force actually depends upon which charge we're talking about. So let's be very specific and talk about the force on charge 2. Now, fortunately, from Newton's third law, of course, once we know the force on charge 2, the force on charge 1 will be equal in magnitude, but opposite in direction. So it suffices just to have a formula for the force on charge 2. The next thing and detail we need to get into is the fact, as I just referenced, that these forces have different directions. That means that these forces are vectors, so I better denote this properly as a vector. And the formula that I have here now is actually only telling me the magnitude of the force. In a moment, we'll have to figure out the direction of the force in terms of these given charges and these given vector locations. But first, let's investigate a little bit the remaining terms in the formula for the magnitude. The first term, K, is Coulomb's constant. Now, there are a whole bunch of different constants, K, that can appear in a physics course, right? You're familiar with the spring constant, frequently, which is called K. There's something called Boltzmann's constant in other courses that are also called K. So to be formal and to be very careful about things, we'll always try to include a subscript on K, a capital C subscript. That means this is Coulomb's constant, the constant actually that goes into Coulomb's law. Then we have the product of the two charges, and this R represents the distance between those two charges. So if I go back to my diagram then, I'm going to consider the distance between them. Let me draw this here as a dashed line. And that distance I'll call R, but now this distance should refer to the charges whose distance I'm measuring. So I'm going to call this R sub 2, 1. And that order will become important later on, even though it seems a little backwards right now. So that's the distance between the two charges. And in consequence, let me write this here then as R2, 1. Very good. Now, the last thing we need is the direction. Now, if these were two positive charges, as we were just referencing, then the force on charge 2 would be outward. It would be in this direction, directly away from Q1, actually along the same line as Q1. So I want to define a vector which points along this line that goes from Q1 towards Q2. And the way I've just said it, if you think about vector algebra, gives us the definition of that vector. Remember how vectors add head to tail. So what we would really like, if you will, is if I made this dashed line that I'd indicated actually a vector pointing in this direction, right? That vector then points in the direction that I want, right? Directly from Q1 towards Q2, and I can figure out what this vector is, because after all, look at this. If this is vector R1, and I add to vector R1 this dashed vector, the vector I'm looking for, the result will be R2. So if you think about this a little bit, what I'm really saying is this dashed vector is the vector R sub 2 minus vector R sub 1. And the way we can see this, for instance, is that if I check my vector algebra, R sub 1 plus then my dashed vector here should give me R2. And if I write down now the formula I've given you for that dashed vector, R sub 2 minus R sub 1, and I carry out, that addition, well, yeah, sure enough, the R1s will cancel out. They're going to subtract out, and I'll just be left with R2, which is what I needed to get. So therefore, I've now defined this dashed vector. What I need to multiply here in order to include that as a direction, though, isn't this vector, because this vector actually has a length. I need a unit vector that points in the direction of that vector. So, to compute that then, what I can do is I can take that difference vector, R2 minus R1. That vector now, of course, has some length associated with it. To turn it into a unit vector, a vector of unit length, I need to divide the vector by its own length, R2 minus R1, its magnitude. That then will give me a unit vector that points from charge 1 towards charge 2. So that would be a unit vector. I'll call this R hat. And we have two ways of writing this unit vector. Sometimes, if we want to be very explicit, it helps to write it with a little arrow, R from 1 going towards 2, so we know what direction we're referring to. And what's nice, if you write it this way, you'll notice it gives you a little mnemonic for remembering the formula. It's R2 minus R1. It's not the other way around. And this then preserves that order. R, first the 2, the arrow is sort of like the minus sign, and then the 1. And this is why it's important to write that order down properly, R, 2, 1. Now, it becomes cumbersome after a while to keep writing these little arrows, so this is more typically written as R hat 2, 1. That's the unit vector then, to which I multiply my magnitude to achieve my final force. So this will be R hat 2, 1, where I've given you the definition of R hat 2, 1 down here. So this then is a complete mathematical specification of the force on any charge 2 due to the presence of any other charge 1, where the two charges are sitting at vector locations R1 and R2.